Have you ever wondered how secure your Python code really is? In the world of programming, Python has emerged as a popular choice among developers for its readability, versatility, and vast libraries. But just like any other language, Python too has its share of vulnerabilities. These are the cracks in your code that can be exploited, leading to what we call Python exploits. Now, why should this matter to you? Well, Python exploits can lead to damaging consequences, from data breaches to system crashes. Therefore, it's crucial to understand these vulnerabilities and how to prevent them. In essence, secure coding practices aren't just a good idea, they are a necessity. Neglecting these vulnerabilities could put your entire system at risk. But fear not, because today, we're embarking on a journey to uncover the intrigue of Python exploits. So, are you ready to delve into the world of Python exploits and learn how to identify and exploit a common Python vulnerability? To understand how to exploit Python vulnerabilities, we first need to understand what they are. At its core, a Python exploit is a piece of code that takes advantage of a flaw or vulnerability in a Python application. It's like finding an open window in a locked house, a way to get in, bypassing the usual security measures. There are several types of exploits, each unique in how they attack these vulnerabilities. One such type is code injection, which is exactly what it sounds like. It's when an attacker injects malicious code into a Python application, often through user inputs or manipulated files. This injected code can then be executed by the application, allowing the attacker to manipulate the system or access sensitive data. Then we have buffer overflow exploits. They occur when an application receives more data than it can handle, causing it to overflow its allocated memory space. When this happens, an attacker can overwrite the application's memory with their own code. This can lead to system crashes, data corruption, and even give the attacker control over the system. There's also the concept of race conditions. This is when the timing or sequence of processes affects a program's outcome. An attacker can exploit this by controlling the sequence of events in a program, leading to unexpected and often damaging results. And of course, there are many other types of exploits out there. But for the sake of time, we'll be focusing on code injection exploits in this tutorial. Why, you may ask? Well, code injection is one of the most common types of exploits, and understanding it is essential to both exploiting and protecting Python applications. So, in a nutshell, a Python exploit is a door left ajar, a weakness that can be used to manipulate a Python application. The more we know about these exploits, the better we can protect our applications from them. Now that we understand what a Python exploit is, we can start looking at how to identify them. Identifying vulnerabilities in Python code is the first crucial step towards securing your applications. While Python is renowned for its simplicity and readability, it's not immune to security vulnerabilities. So let's talk about how you can spot potential weaknesses in your code. The first telltale sign of vulnerability is the use of the eval function. In Python, eval evaluates a string as code, which can open the door for code injection attacks if not properly sanitized. For instance, if you're using eval to evaluate user input without any form of validation, you're essentially giving a free pass for malicious code to execute in your application. But how can you spot this? Look for instances where eval is used in combination with user input. This could be in the form of direct input from a user, file data, or even data retrieved from a database. Next, let's touch on insecure dependencies. Python, like many other programming languages, allows the use of external libraries and modules. While these can speed up development and extend functionality, they can also introduce vulnerabilities if they're outdated or poorly maintained. Using tools like PyUp or Safety can help you identify and manage these insecure dependencies. Additionally, be cautious of insecure file operations. If your application reads, writes, or deletes files based on user input, you could be opening yourself up to path traversal attacks. This is where a malicious user manipulates input to gain access to files or directories they shouldn't have access to. Lastly, keep an eye open for weak cryptographic practices. If your application involves any form of encryption or hashing, make sure it's done right. Using weak or outdated algorithms, hard-coding keys, or failing to manage keys securely can all lead to vulnerabilities. With these tips in mind, you are now equipped to identify potential vulnerabilities in your Python code. Remember, the goal isn't to eliminate every single vulnerability. That's nearly impossible. The goal is to understand, manage, and mitigate risk effectively to protect your application and its users. Now, let's switch roles for a moment and think like an attacker. How would one exploit these vulnerabilities? Imagine you're dealing with a Python application that utilizes user input to perform certain functions. This is where code injection vulnerabilities can come into play. An attacker can manipulate the input in such a way that it runs malicious code within the application. This is often seen in applications that use the eval function, a Python feature that allows the execution of arbitrary Python expressions from a string-based input. Let's take an example. Suppose there's a calculator application that uses the eval function to calculate user-provided expressions. An attacker could input a seemingly innocent mathematical expression, but append it with a malicious Python command. For instance, they could input 2 plus 2, import os.systemarm.rrf. This would not only calculate the sum of 2 and 2, but also execute the following malicious command, potentially causing significant damage to the system. This is just a simple example. In reality, attackers can craft more complex and destructive code injections, making it imperative for developers to understand this threat. Another common vulnerability in Python applications is insecure deserialization. This occurs when an application deserializes data from untrusted sources without proper validation or sanitization. An attacker could exploit this by injecting malicious data, which, when deserialized, can lead to code execution or even complete takeover of the application. To illustrate, consider an application that uses Python's pickle module for serialization and deserialization. An attacker could craft a malicious pickle object that, when deserialized, executes arbitrary code. In conclusion, exploiting Python vulnerabilities largely relies on manipulating untrusted user input and exploiting features like eval or insecure deserialization. By understanding these potential threats, developers can better anticipate and mitigate these vulnerabilities. Remember, understanding these exploits is not about misusing this knowledge, but about knowing how to protect your applications. Now that we know how to identify and exploit vulnerabilities, how can we secure our Python applications? Well, the first step is to adopt secure coding practices. One of the key aspects of secure coding is input validation. This involves ensuring that the data your application receives is what it expects. For instance, if you're expecting numerical input, make sure that's what you're getting. This can help avoid injection attacks, where an attacker tries to insert malicious code into your application. Another aspect of secure coding is the use of secure coding libraries. These are libraries that have been designed with security in mind and can help you avoid common pitfalls. They take care of the low-level details, allowing you to focus on the high-level logic of your application. One example is the requests library for handling HTTP requests. It's much safer than using the built-in erlib library, as it automatically checks for secure connections and prevents certain types of attacks. Now let's talk about code reviews. Regular code reviews are crucial for maintaining the security of your Python applications. They provide a second set of eyes to catch potential vulnerabilities that you might have missed. This is where having a diverse team can really pay off, as different people may spot different issues. And remember, code reviews are not just about finding bugs. They're also an opportunity to learn from each other and improve your coding skills. Vulnerability testing is another essential practice. This involves actively trying to find vulnerabilities in your code, either manually or using automated tools. It's like a self-imposed hackathon where the goal is to break your own code before someone else does. It's a proactive approach to security, and it can save you a lot of trouble down the line. Finally, remember that security is not a one-time thing. It's an ongoing process that involves constantly updating your knowledge, reviewing your code, and testing for vulnerabilities. It's a journey, not a destination. By following these practices, you can significantly reduce the risk of Python exploits in your applications. So, we've covered quite a bit about Python exploits today, haven't we? Let's take a moment to recap. We started off by delving into the intriguing world of Python exploits, exploring the different types and how they can pose a threat. From there, we journeyed into the process of identifying these vulnerabilities in Python code, learning how to spot the red flags and potential weak points. Moving on, we examined how these vulnerabilities can be exploited if left unchecked, reinforcing the importance of addressing them promptly. Finally, we looked at how to secure your Python applications, equipping you with the tools and strategies to safeguard your code against potential exploits. With this knowledge, you are now better equipped to write secure Python code. Remember, the key to security is constant vigilance and proactive measures. Happy coding.